Okay, I wanted to do a couple of examples about potential, and then we're going to talk a little bit about electrical potential energy and how it applies to one of my favorite ideas in physics, conservation of energy. For starters, let's look at this example here. A 10 Coulomb particle's energy at position I is 20 joules. So when it's here, it's got an energy of 20 joules. The particle's energy at position F is 5 joules. So when it's right here, it's got 5 joules of energy. Now, the problem asks, what would happen to the energy if instead the particle had a different charge? If the charge was half as much, then what would the energy be? Well, I hope just intuitively it seems reasonable that if it's got a smaller charge, then it's going to have a smaller amount of energy. And maybe we could even guess that if it's half the charge, it might have half the energy. But let's make sure. Let's do the math and let's make sure that that's the way it's going to work out. So in order to do this, let's find what the potential is at I and what the potential is at F. Now notice that's different from potential energy. Remember, potential and potential energy are different. So we had this equation that said that U equals Q times V. The potential energy is equal to the charge times the potential. That means then, of course, that the potential is equal to the potential energy divided by the charge. And so that means that the potential at point I is simply 20 joules divided by the charge, which is 10 coulombs. Two volts. The final is 5 joules divided by 10 coulombs equals 1/2 of a volt. So that's 0.5 volts. All right, 0.5 volts. Now, let's look at this. Does this potential require there to be a charge at this location? No, there doesn't, right? This potential 2 volts exists at this point right here, whether there is a charge there to experience it or not. In essence, this 2 volts is created because this charge right here is there, right? So this charge right here creates a potential which fills the space around it. And the potential right here is 2 volts, whether there's a charge there or not. Now, if I put a 10 Coulomb charge at this location of 2 volts, then it has an energy of 20 joules. But what about if the charge was a 5 Coulomb charge? Well, let's see. For 5 coulombs, we have the initial potential energy is equal to, again, we'll use this equation here, the charge. Now we have a 5 Coulomb charge, and we're going to multiply that by 2 volts. We get 10 joules. So again, same potential, different charge gives us a different amount of potential energy. And again, you maybe could have guessed this initially. Half the charge gives us half the potential energy. How about at the final point? At the final point, that's going to be 5 coulombs times 1/2 of a volt gives me 2.5 joules. Okay, so again, half the charge, half of the energy. And so one of the points I want to make with this example, the mathematics is pretty straightforward, right? The point I want to make is that the potential is something that's defined at a certain point. The potential energy is the energy of a charge at that point. Right? So potential energy, different, but very closely related. Let's do another example. Okay, so let's look at this example. We see a 10 Coulomb particle's energy at position I is 40 joules, and its position at F is also 40 joules. What is the electric potential at points I and F? Well, we could think about this. First of all, why does its potential energy not change as it's moved from I to F? Well, notice it's not getting any closer or farther from the positive and the negative charges. Notice that at position I, a positive charge would experience a force to the right, and if I moved it to F, notice that the angle between the displacement and the force would be 90 degrees. Again, no potential energy is created when the force and the displacement are perpendicular to each other. So they have the same potential energy. We would guess then that they must have the same potential. Points I and F must have the same potential. What is that potential? Well, we know that V, the potential, is equal to the potential energy divided by Q. And so this is a straightforward problem again. We have 40 joules divided by 10 coulombs. So our potential then is 4 volts. Again, fairly straightforward, but it's a tricky concept. So I think it's worthwhile to spend some time doing some problems where the math is straightforward so that we can really focus on this concept. Okay, one of my favorite ideas in all of physics is conservation of energy. And if you'll recall from last semester, conservation of energy says that in any closed system, the total energy before something happens, before some interaction, is exactly equal to the total energy in the system after that happens. Energy can change forms, but it cannot ever be created or destroyed. It's such an amazing idea. You know, if we think about the energy I'm using to stand up here and speak to you, it's chemical energy that I'm burning in my body, right? My body is converting glucose into oxygen, is combining oxygen and glucose to create carbon dioxide, water vapor, and energy. Where did that energy come from? Oh, it was stored in a plant last summer, probably. How'd the energy get into the plant? Oh, it came from the sun, right? In the sun, nuclear processes are releasing tremendous amounts of energy. Anyway, conservation of energy is a pretty cool idea. We can apply it to electrical concepts in the same way that we applied it to mechanical concepts last semester. So, confined then to electrical type situations, we can sort of simplify the conservation of energy that we talked about last semester. And so we'll reduce it to where we only have gravitational potential energy and kinetic energy. So recall from last semester that conservation of energy, it started out with this basic idea that energy is never created or destroyed. To turn that into math, we just say that the total energy in some system, initially, before something happens, anything, is equal to the total energy in the system after that happened, whatever it was that happened. And so recall that last semester we talked about all different kinds of energy, right? We can have kinetic energy, gravitational potential energy, spring potential energy. Heck, we even started talking about thermal energy. So we could have heat, we can have chemical energy. A battery actually stores chemical energy. Nuclear energy gets released in a nuclear reaction. All kinds of energy that could go in either side here. Now, what we're going to do here is we're going to constrain ourselves this semester, and we're going to talk about kinetic and electrical potential. So we could say, okay, this would be then kinetic initial plus U electric initial must equal kinetic final plus U electric final. And so if you'll turn your attention now to the PowerPoint here, I've got a list of 3 steps, kind of 2, really. I'm not sure that should be a separate step. But very similar to what we did last semester when we solved conservation of energy problems. First, we're going to draw before and after pictures. So this is a quick sketch of the situation before something happened, and a quick sketch of the situation after it happened. And now we're going to apply the conservation of energy. This says the total energy finally must equal the total energy initially. Now notice the difference between this PowerPoint equation and what I've got here is I've simply plugged in Q times V equals U. And we get this equation on the PowerPoint. Now a couple of notes. You may need to calculate the initial and final potentials, or they may be given. For starters here in these next few problems, we're going to give it to you, but eventually you may need to calculate it using some other things. And as I stated, Kf and Ki are the initial and final kinetic energies. Let's try an example. A proton has a speed of 3.5 times 10 to the 5th meters per second at a point where the electrical potential is 600 volts. It moves through a point where the electric potential is 1,000 volts. What is its speed at this second point? So this is a conservation of energy problem for sure. Telling us that it's a proton tells us its charge, and it tells us its initial and final potentials, so we know its initial and final potential energies, or at any rate we could find them very easily. Of course, its speed is related to its kinetic energy, and it's asking for its final speed. So this is definitely a conservation of energy problem. We'll want to start with this equation. But before we do that, we should probably draw a quick before and after picture. So our initial point here at our initial point, our proton is moving 3.5 times 10 to the 5th meters per second. And the initial potential is 600 volts. It's going over here to the final point. At the final point, we want to know what is V final. Its final velocity. And we know its potential. The final potential is 1,000 volts. Okay, so now we're going to apply the conservation of energy equation. Final kinetic energy plus QV final equals kinetic energy initial plus Q times the initial potential. Now what we're looking for is, of course, in the final kinetic energy, we're looking for the velocity. So we're going to have to plug in our equation for the kinetic energy. Now I know everything in this equation except for V final, and so we'll go ahead and do some quick algebra. So in here what I've done is I've taken my V final to the other side, factored out a Q, multiplied both sides by 2, and divided by M. Multiplied by 2, divided by M. We ended up with this. Now I will take the square root of both sides. And I get that. And so now I could just plug in my numbers. Okay, now I can run my calculator. So, we got a final velocity here. And what happened? The proton slowed down. It went from 3.5 times 10 to the 5th meters per second to 2 times 10 to the 5th meters per second. Does that make sense? I think so. When a proton goes from low potential to high potential, it's going uphill in our electrical landscape. A positive charge moving uphill in our electrical landscape should slow down, just the same way that a ball kicked up a hill will slow down. Okay, so now let's look at part B. What's different for part B? Well, we have an electron, but it's still moving from 600 volts to 1,000 volts. The proton slowed down when it went from low potential to high potential. What do you think the electron will do? Will it slow down or speed up? Let's see. Going through here, we have the same exact initial situation, same final situation. We're still going to use conservation of energy. Our algebra looks exactly the same. It's not until we get all the way down here that I have to change anything for this second part. So let's see. We have a different charge and a different mass. The mass is much, much smaller. An electron's about 1/2000th the mass of a proton. And so we'll need to change that. And an electron is negative. So we throw a negative sign in front of the charge. And then when we run our calculator, we get 1.2 times 10 to the 7th meters per second. So we see that the electron actually sped up when it went from low potential to high potential. So that's sort of interesting. If it sped up, its kinetic energy increased and its potential energy decreased. Whereas for the proton, it slowed down. So its potential energy increased and its kinetic energy decreased. Yet for both of them, they went from low potential to high. Don't forget this equation here. U equals Q times V. Notice that if Q is positive, and increasing potential means an increasing potential energy. If Q is negative, and increasing potential means decreasing potential energy. Of course, if Q is 0, a changing potential means no change in potential energy. That would be like a neutron.